Hello physics students, we are working on chapter 4, looking at circular motion problems from the homework. Just going to be going through some homework problems that you guys texted me about wanting to go through. So this is number 3, that's the first one we're going through. We have a bicycle tire that's spinning around. There's a pebble stuck in the tread of the tire. We're talking about the motion, the circular motion of that pebble that's going around the outside part of the circle as it goes around. So the radius is given. It's actually giving me the diameter is 70 centimeters, so the radius is 0.35 meters. Let me write that better. The radius is 0.35 meters. It also tells me that the pebble goes by 3 times every second. So that's omega. That's the angular velocity. It's 3 revolutions per second. All right. Part A asks for the pebble's speed. So I believe that's asking for the linear speed of the pebble. So if the pebble were to come out of the tire at a particular moment, what linear speed would it be going? We can get that if we know the angular speed and we know the radius, then we can get that. Anytime you know the angular entity, all you have to do is multiply by r to get the linear entity, or you might call it tangential entity. So if we know the angular displacement, we can get the linear displacement by multiplying by r. If we know the angular acceleration, we can get the linear acceleration by multiplying by r. If we know the angular velocity, omega, multiply by r to get the linear velocity. And that's what we have going on here. So all we have to do is fairly straightforward. But one thing I should say is that omega times r equals the velocity when omega is in radians. It has to be the case that the unit for omega is radians per unit of time. Alright, so let's get omega in radians right here. 3 revolutions per second. I'm just going to change the revolutions to radians. 1 revolution is 2 pi radians. And that's really all we have to do. We can let it be radians per second. So that's 6 pi radians per second. So then 6 pi times 0.35 meters will give me the velocity. So that's radians per second times 0.35 meters will give me the velocity in meters per second. So let me just do a little calculation on my calculator. Six times pi times 0.35 equals 6.6 meters per second. Remember that radians is really a unitless unit. It's a pseudo unit. So we can just have meters per second from our unit analysis here. Part B, the pebble's acceleration. The acceleration that it wants is the only acceleration that's going on here, because the pebble is not speeding up around the circle, but it is changing direction. So the velocity is changing its direction, which means it has to have an acceleration. That acceleration is called centripetal acceleration. Another name for it is radial acceleration. If I could draw a picture of it, well, I've got a picture right here. The acceleration of an object going around a circle, if it's just uniform circular motion, meaning it going in a constant velocity around the circle, constant angular velocity, the acceleration points toward the center of the circle. It points in the direction of the radius toward the center of the circle. That's why it's called the radial acceleration. It's going toward the center, which is also why it's called the centripetal acceleration, center-loving or center-seeking acceleration. Positive, the direction of this acceleration can have a positive or negative direction. Toward the center is positive. away from the center is negative. So it doesn't matter where it is on the circle, you're going to define the positive direction for acceleration toward the center of the circle, and negative direction for that acceleration away from the center of the circle. So that's just some extra information for you. But to get the centripetal or radial acceleration, it's just going to be either omega squared r or v squared over r. Either way you want to do it. And we have the v right here. We have the omega right here. So we could go either way with it. I think I'll just say omega squared r, 6 pi squared times 0.35. That's radians per second. And that's meters. So it's going to turn out to be meters per second squared, as it should, for acceleration like that. And if we do that little calculation in our calculator, 6 squared times pi squared divided by 0.35 equals 124.4 meters per second squared. Okay. Next one, number 4. Some work I did on this earlier when I tried to record this earlier, and the pen didn't work on me too well. Got a new battery for it, so it's working good. Alright, a bicycle wheel is rotating. It gives us the omega. If it will cooperate, it gives us the omega. That's 46 revolutions per minute. It gives us also, it says that the bicyclist starts pedaling harder, giving it an angular acceleration. So not only is it going around the circle at a constant velocity, actually that angular velocity is increasing. We have an angular acceleration. That's alpha. Alpha is 0.49 radians per second squared. Alright, I already know here I'm going to need to get consistent units, so I've got radians per second squared in alpha. I've got revolutions per minute in omega, so I want to change this omega to radians per second. So 1 revolution is 2 pi radians, and 1 minute is 60 seconds. So we're left with radians per second. That's what I want. And that is a little calculator work here. 46 times 2 times pi divided by 60. I get 4.8, around 4.8 radians per second. Okay, so it's asking me the wheel's angular velocity in RPMs 6 seconds later. So after this bicyclist starts pedaling harder and gives it an acceleration we've talked about, what does the velocity get up to after 6 seconds? So this is, for linear stuff, if we know the acceleration, then we go from there. The antiderivative gives us velocity, and the antiderivative of that gives us position. Well, for angular stuff, it works the same way. Start with alpha, which is just a constant 0.49, and then the antiderivative of that is velocity, so VF equals the antiderivative of this, which is 0.49 t, plus the initial velocity, which we know to be 4.8, and that will give us the final velocity, because we know the time. So let's just calculate this. VF equals 0.49 times 6 plus 4.8. Little calculator work here. 49 times 6 times, plus 4.8 is 7.74 meter. Nope. I shouldn't have said v. I should have said omega. I'm sorry. It's not the linear velocity, it's the angular velocity. The angular velocity is 7.74 not meters, but radians per second. So the antiderivative of alpha gives us omega. So that's angular acceleration going toward angular velocity. And that's our answer for part A. Part B says how many revolutions. Let me see, make sure I've answered this correctly. Express your answer in revolutions per minute. What I've got is radians per second. So I haven't quite answered the question the way they want me to. If it wants RPMs, I'm going to do 7.74 radians per second. Change it to RPMs. That's going to be 2 pi radians for 1 revolution and 60 seconds for 1 minute. And that gives me revolutions per minute. So I know you know how to continue to do that. Use 7.74 times 60 divided by 2 divided by pi. That will give you the answer in revolutions per minute. So I'm just going to skip that part. Nothing new there. It's just doing a unit conversion. Alright, if I want to know part B, how many revolutions does the wheel make during this time? That's actually an angular displacement. So if I want to know the angular displacement, then I'm doing the antiderivative of omega to get theta. Theta final is equal to the antiderivative of this omega, so that's 0.49 t squared over 2. So that would be 0.245 t squared. All I did was 0.49 divided by 2 plus 4.8 t plus the initial theta, which is, we can just say is 0. And that will give us our final theta, which is the amount of revolutions, or actually it's the amount of radians that the wheel will turn through during that time of that acceleration. So if I just plug in 6 for t, .245 times 6 squared plus 4.8 times 6, that gives me little calculator stuff here. 37.62, and that's radians. So if it wants revolutions, I've just got to do a unit conversion. 37.62 radians, and there's 2 pi radians in 1 revolution. So I just divide that by 2 and divide it by pi, or divide it by the whole 2 pi. And that will give us our answer to part B. Alright, I'm going to skip over that part. Alright, we're now looking at number 5. Alright, number 5, I really didn't mean for number 5 to be on this assignment, because it is not circular motion. It is projectile motion. But it's on there, and why not? Let's just do it. So, it is a fairly difficult problem, but that's what this help is for. So, I'm just going to do a little geometry real quick. Knowing I already kind of got to understand this problem, we're trying to clear this roof, and we got to just barely clear it according to the problem. The minimum speed and angle that will clear that roof and get to the friend. So, I'm going to do a little geometry to figure out how high that roof really is. So, you got this roof part of the house. It's 6 meters on that triangle, on the base of that triangle. If I cut it in half right here for a 90-degree angle, it tells me this is a 45-degree angle here for the pitch of the roof. That means this is also 45. And if I cut this thing in half like I just did, this is 3. Which means if this is a 45, 45, 90 triangle, this other leg also has to be the same. It has to be 3 also. So this is 3 units high right here, 3 meters high. And this whole thing right here is also 3 meters high. But the ball starts out already 1 meter above the ground and hits over here 1 meter above the ground. So I'm just going to cut a meter off of this and pretend like that is the ground. So really, this is 2 and this is 3. So that height right there, this height is 5 meters from where that ball starts and stops. All right. Okay. Now, here goes my same stuff I always do. The vertical acceleration is negative 9.8. The vertical velocity is negative 9.8 t plus the initial vertical velocity. The vertical position is negative 4.9 t squared plus the initial velocity times t plus the initial vertical position, but I'm just going to call that 0. Okay. So we know that the height that we want to get that ball is 5. So I'm going to rewrite this as 5 equals negative 4.9 t squared plus VIYT. And we also know that when it gets to that height, that the vertical velocity at that moment when it reaches its apex is 0 for a split second. The horizontal velocity is not 0, but the vertical velocity at that moment when it reaches its apex is 0. Alright, so I've got a little system of equations here. I've got t, and I've got VIY, and those are the same in each of these equations. The moment it reaches 5 is the moment the velocity is 0, so the time's going to be the same in each of these equations. The velocity and the initial velocity is not going to change in the equations, the same initial velocity. So I should be able, in theory, to solve this system of equations. What I'm going to do is I'm going to solve for VIY here. VIY is equal to 9.8 t. All I did was just get the VIY by itself by moving 9.8 t over. And then I can substitute that into the VIY in the other equation. So that gives me 5 equals negative 4.9 t squared plus 9.8 t times t. Alright. That's negative 4.9 t squared plus 9.8 t squared. So that gives me 5 equals positive 4.9 t squared when I add my like terms. Divide by 4.9. Okay, and take the square root. And I get t to be 1.01. Okay. Then I plug that into the t back here to get the VIY. So VIY is equal to 9.8 times 1.01, and that turns out to be 9.9. Okay, so that's my initial vertical component of velocity, 9.9 meters per second. Now for the horizontal. Horizontally, A is 0. So the final velocity in the x direction is equal to the initial velocity in the x direction. And the final horizontal position is equal to the antiderivative of that, which is VIXT, plus the initial horizontal position, which we could just call 0. So there we go. All right. I know that the final the final horizontal position when it reaches this apex is 6 plus half of 6. So 6 plus 3 is 9. So the final horizontal position when it reaches this same spot that we've been talking about is 9, and that equals VIX times that time we already know, 1.01. So divide by 1.01, and we get 8.9 for the VIX. So I've got my vertical component of velocity, I've got my horizontal component of velocity. So the overall velocity is equal to the Pythagorization of that stuff. So I could say it's 8.9 squared plus 9.9 squared. And that turns out to be 13.3. And that is my answer for part A. For part B, the angle is the arctan of the vertical component over the horizontal component. So 9.9 over 8.9. And that turns out to be about 48 degrees. That's my answer to part B. So I hope that helps you to get number 5 right. Alright, this is number 15. Alright, it gives me, the figure shows the angular velocity. So I've got omega, the angular velocity, a graph of that, and it says how many revolutions does the object make during the first 4 seconds. Now, this is a pretty straightforward problem if you realize this. The revolutions that it's making during that time is the angular displacement, or you could think of it as the angular position, the final angular position. And that is just, so if we're looking at angular velocity, and we want to know something about angular displacement or position, then we're looking for what in this graph? The area. So I just got to do the area here. Alright, so if I do this triangle's area plus this rectangle's area, so the triangle area is 1/2 times 2 times 20. That is 20. And the area of the rectangle is just going to be 2 times 20, which is 40. So add that together, it should be 60 radians. Yeah, so the answer to that problem should be 60 radians. And problem 16, we're looking at what? We're looking at the angular acceleration. It's asking about angular velocity. So if we're looking at acceleration and we want a graph of that and we want to know velocity, what are we looking for about that graph? We're looking for area. And it says at time t equals 1 second. So that's, we're not doing the whole triangle. We're just doing this part of the triangle. Alright, so I'm just blowing this up because it's kind of hard to see where this happens. Alright, so I think what I'm going to do is break this up into this rectangle and this triangle. So we're only looking for that area. We're not looking for the area of this whole the whole triangle here, because we only want to know it up to 1 second. So we got to cut it off right here. So there's multiple ways you could do this area. You could do this whole trapezoid right here, if you know the formula for the area of a trapezoid, or you could do the area of the whole big triangle and subtract the area of this little triangle. That's another way to do it. But the way that I'm going to do it right here is by breaking this area up into a rectangle and a triangle. So the area of that rectangle, I do believe is, see, that's what's hard because it's not right on a number. I think we call the length 1, and the height here is 2.5, I think. So that's 2.5. And then the area of the triangle is 1/2 times the base, which is 1, times the height, which is, if we start here and go to here, from 2.5 to 5, that's 2.5. So that's going to be, 2.5 is the same thing as 5/2. So that's going to be 5/4. Or we could say 5/4 is 1.25. Just a second. So if I'm right, if I just did my little math calculation right here, then that's going to be 3.75 when we add those together for the omega. I just want to go type that in and make sure that that is correct. Okay. 3.75 radians per second. Oops. Submit. That is correct. Good deal. Alright, this is number 18. So I am given the omega, and I'm given the time. So if we start with an acceleration, we know that there is an acceleration. It's actually angular acceleration. I should write it alpha. Angular acceleration alpha. And then omega is the alpha times the time plus the initial omega, but we can say that the initial omega is from rest, so it's 0. So, what do we know? We know omega. We could put omega here in radians per second, or we could leave it in RPMs and let our alpha also be in RP something. Maybe to be safe, I'm just going to make it be in radians per second, just to work in standard units for each problem. 2,000 revolutions per minute. There's 1 revolution for every 2 pi radians. And there is 1 minute for every 60 seconds. That leaves me with the radians per second. So if I calculate that correctly with a little calculator at work here, that's going to be 4,000 times pi divided by 60. I get 209.4 radians per second. Alright, and so now 209.4 is omega. I'm looking for alpha. 4.4 seconds is the time. All I got to do is divide to get alpha. And that is 47.6. Radians per second squared. That's the angular acceleration for that fan. Alright, and I think this is the last one that I was asked about. So, it's a slightly difficult one, just because we have 3 kind of phases for this problem. How many revolutions does it make? So it's asking us for the angular displacement, theta. But we have 3 phases. One phase where it's accelerating, another phase where it's going at a steady speed, and then the last phase where it decelerates to a halt. So we got to figure out how many revolutions it makes during each of those phases where it has different angular accelerations during each phase. So let's go phase 1 first. Phase 1. The angular acceleration is something that I don't know. I'm just going to call it alpha for now. The omega final is equal to alpha t plus the omega initial, and the omega initial here is 0 because it starts from rest. Alright. I know the time, and I know the omega final, so I can find acceleration now, which I'm going to need. But first, units. 500 revolutions per minute. let's go to radians per second. Okay. Calculator tells me 500 times 2 times pi divided by 60 is 52.4. Radians per second. So 52.4 radians per second equals alpha times 1 second. Divided by 1 obviously doesn't do a thing except tell us that alpha equals 52.4 radians per second squared, because we divided by 1 second. So it's radians per second squared for the alpha. Alright, now that was an antiderivative. Now antiderivative of that is the angular position or displacement theta. That's going to be 1/2 alpha t plus omega I t, which is 0, plus theta I, which is 0. So that's just going to be 1/2 times 52.4 times 1 second. Sorry, 1/2 AT squared, isn't it? So times 1 squared, which will, 1 squared is just 1 anyway. So this is going to be half of 52.4, which I believe is 26.2 radians. So for phase 1, we've got 26.2 radians. That is the angular displacement during the first phase of circular movement there. Alright, phase 2. We're going a steady 3. Omega is, a steady 500 revolutions per minute, which we already figured out. We're going that steady 52.4 radians per second for 3 seconds. Alright, this is simple. This is just omega is a 52.4 constant. The antiderivative of that, theta, is just 52.4 times t plus theta initial. We're just going to call that 0 for phase 2. So that's just going to be 52.4 times 3, which is 157.2 radians. So phase 2 is 157.2 radians. And now let's get phase 3. Phase 3 we do have an alpha, which we don't know yet. We know we have so the final omega is just going to be alpha t, and plus the initial omega. In this case, the final omega, since it comes to a halt, the final omega is 0, and the initial omega is that 52.4 radians per second that it started with when it entered phase 3. The time is 2 seconds. I can solve for alpha. Just move the 52.4 over. Divide by 2. Alpha is negative 26.2. Okay, so now if I go back to this formula to do the antiderivative to get theta. 1/2 alpha t squared plus omega I t. We do have an omega I in this case. Plus theta I, we could just let that be 0 for phase 3. So let's plug in what we know. 1/2 times negative 26.2 times 2 squared plus 52.4 times 2. And I could just do that calculator work. To get 0.5 times negative 26.2 times 4 plus 52.4 times 2, I get 52.4. So phase 3 is 52.4 radians. So if I add all 3 of these up to get the total number of radians that DVD turned in that time period, that is going to be 26.2 plus 157.2 plus 52.4. I get 235.8 radians. This is asking me how many revolutions, so I just need to do a little unit conversion here. 2 pi radians for 1 revolution. It gives us revolutions. So I just got to divide my answer here. Uh, 235.8 divided by 2 divided by pi to get 37.5 revolutions. I'm going to type this in and make sure it's right. And it is right. So, great. Hopefully that gets you guys the help you need on that homework. Hopefully you're starting to understand some things and get just a little bit more comfortable. I know it takes some time to get used to circular motion and all the symbols and all the concepts and thinking about how things are working in circular motion. But hopefully, again, this helps you get this homework done well. See you next time.